So this time we'll consider exploiting memory hierarchy, right? We'll be doing caches actually, right? So we already have ideas on memory, the different types, DRAM and SRAM. And I mean, the way the capacitors are arranged and everything was in part of the DSD2 course. That was not what we really want here. But what we are really wanting is that we want large and fast memories, right? But the whole truth is that larger memory and fast memory, they are like trade-off, right? The when your memory is very large, right, it can't take and it's also fast as well, right? The price will go high, right? So it's either it is very large and slow, or it is very fast and slow, right? So those are trade-off. But we also want to make it see that it seem to the user that like his memory is very fast, right? So we exploit memory hierarchy, right? And the hierarchy includes the use of memories at different levels, right? So that access will be fast, right, for the user. But we'll see. So in anytime you see box, right, it's just a unit of data copy, right? So when you see multiple of them, then we are using multiple blocks of data copy, and we'll see them largely when we are dealing with the caches, right? So for now, just take notes. Now, locality. Locality is just the principle that um, when we reference something, there's the likelihood to reference it again. So what locality is saying that, um, for example, when I'm executing a program, right? When I'm executing a program, you see there are two types of locality actually, right? We have spatial and temporal. Temporal means that like a variable, right? There's a possible possibility of using a variable because most of the time you do x plus 1 or x plus plus, like you'll be increasing an x or increasing commonly, right? There's also the spatial one. The spatial one is like when um, I take memory, right? When I take a large block of memory, right? There's the possibility that if I access this one, I'll access this one, I'll access this one. For example, an array, whereas that it stores things in a contiguous form, right? So if some way somehow I have already fetched, if I was coming to fetch the first one and I fetch all the four, right? There's a high chance that the next time I'll not need to come back to memory to come and fetch because I already have all the four, right? That's locality, right? So it is a concept which exists in programming that in memory access there's a possibility that you access several memory blocks, right? Because they are close to each other. Or no, the spatial locality is yeah, that's spatial locality, right? And that's spatial locality. Now, we have terminologies, right? Hit and miss, right? So hit means that the data you requested at an upper level, you found it, right? And miss means you did not find it, right? So, for example, the diagram we saw here, right? Maybe you are looking at for data at this level, right? If you find it, it is called a hit. If you do not find it, right, and you come down here to find it, it's called a miss, right? Now, if you don't find it and you go down again, it is a miss, right? But the whole point is that um when anytime you try to hit get a location from an upper memory and you don't get it, right? There is something we call penalty, the miss penalty. The miss penalty is that now that you did not get it, right? You have to pay some price to go lower. So, for example, originally, maybe if it takes 10 cycles to directly go to memory and fetch data, right? And you are using a cache, so it takes 5 cycles, right? Now, you realize that if you go and fetch the cache and you take like 5 cycles and don't find it, right? Now, if you have to go to memory, go and take the 10 cycles again. So your penalty will be that 5 cycles. Do you understand it? So that's the um miss miss penalty, but it's not even got there. So yes, the miss penalty, the time to determine if the access is a miss plus the time to replace, right? So you have to check the time you use to miss plus the time you take to replace. And there's also the hit time, the time to check if it's even there, right? Then there is miss rate, so the frequency at which you are missing, and these are just reading. Now we are going to be using caches, right? Now, there are some things you should also know. Anytime you hear block, right, a block, assume that it is just one location in the cache, right? So a cache, this may be a cache, right? So this is like one block. This is another block. This is another block, right? Now, also assume that every block is storing one word of data, right? Although we might change it later in the course, right? Also assume that it's storing one word. So we are just assuming that our cache is one block is stored 32 bits, right? Because we are using this architecture here. Now, there are several issues. How do we know that an item is in the cache, right? How do we determine? Are we having a hit or a miss? Secondly, how do we even find it if it's in the cache, right? And thirdly, if not, what do we do? Because remember that the control unit for even the single cycle was hard. So now that we are adding caches and everything, if you miss, that means that we have to get some controls, stop the machine, like, so it will be difficult. So solution will depends on the address mapping scheme, right? Now there are several mapping schemes, right? They are actually so far we consider like three, right? There is direct, there is associative, and there is set associative, right? Now the direct mapping scheme um, is such that every address in memory is mapped to a single location in cache. Do you understand? So, for example, this is the cache, right? And you see that the cache is small. The number of blocks here is one, two, three. I think only eight, right? But this is memory. You see, memory is bigger than cache, right? And that is what usually you have. Memory will always be bigger than cache because cache should be small and fast, right? Now, you realize that um the mapping scheme, if we are to use a mapping scheme, which is called direct, right? We are associating every address in memory with only one address in cache, right? Now, this will lead to problems in the sense that there is more items to associate to memory than there's more items in memory to associate to the cache than there is the element in cache. You understand it? So you realize that the algorithm that we can bring, right, would usually map more than one item to the same element. And that's what you can see. So you realize that the gray ones, they are mapping to the same thing, right? The same location because we have made it such that our algorithm which we are using to map it is such that um, everyone wants to be here, right? So the algorithm I used to map this is also such that everyone wants to be here, right? So the algorithm is not bad, right? Because even this one has advantages. The advantage is this in this one is that when you are searching for something, it's fast. You see, these three questions, right? No matter how we implement it, there'll be trade-offs, right? How do we find the item in the cache, right? With this one, because we know that every element is associated with one item, it is easy to find it, right? But um, one disadvantage is that because everyone is also trying to find the same space, most of the spaces will be wasted, right? This is called the direct map, right? Now this is called this one is a trick. There's a trick way, and sometimes people call it one-way set associative, and I'll explain back. Now here is example. So for example, we have a cache, right? And the cache, this is the initial state of the cache, right? This is the initial state of the cache. Now we've not gotten into the cache into details, but just take note. Um, Cache don't store their index actually, like they don't store it in the cache. Just like memory doesn't store its location, we can infer the location from how we access it, right? So this is like the memory locations in the cache, the index, right? And this is called validity level, right? The validity is used to represent the fact that, hey, the data here is good to access. Why? Sometimes when you boot your computer fresh, I mean, all the data in the cache is garbage. So if someone goes to fetch in the cache, it's error, right? It's wrong, right? So the validity is zero. The data here has been fetched from memory, right? So you can use it. Now, we have another thing called the tag, right? Now, we'll see why we need a tag. You realize that because we couldn't use all the bits, the memory address to implement the index, we need some for the tag so that it be unique, right? and the last part is the data, the actual data. So cache will actually store these three things: the validity bit to store the tag, to also store the data, right? Now we are trying to access. So this is a simple cache, right? So this is a simple direct map cache. So we are trying to access data from the cache. Let me see. So the first thing is that our data address, right, is 1110110, right? Now, what most architectures do is that they use modulo to. I should have explained this earlier. Most architectures do is that they use modulo to implement the direct cache to do the mapping, right? So, for example, this is um, 1, here will be 2, here will be 3, here will be 4, here will be 5, 6, 7. So the numbers down there are corresponding. Now, the reason why this one and this one maps to the same place in cache is that this is 1. 1 modulate is what? 1. The location here is what? 1. See, this is, I think this is what? 9. 9 modulate is what? 1. The location here is what? 1. Do you get it? So we are using modulo, right? But the truth is, and it will not be sensible to find hardware specifically for just modulo. So we are just trying to use a cheap modulo function. That cheap modulo function is saying, hey, just check the last 3 bits, right? What the last 3 bits is what the memory and the index in the cache is, right? So you realize that anytime the last 3 bits is 001, 001, it will map to that place. So anytime the last 3 bits, you get it. Now, even though we have seen this, right? So I'm coming to explain why we need the tag. So I've explained the index, right? Now the reason why we need the tag is that um this one and this one, they have the same memory location, right? So at which point will you know that, hey, it is one which is actually memory, or it is what, this 9 which is actually memory? That's why you need the tag. So we store the tag. So the tag will be the remaining bits usually. So the tag will be so the tag for 9 will be 01, and the tag for this will be 00. So that when I check the tag and I know it's 00, then I know, oh, then it is for what? 1. If I check the tag and it's 01, I know that's for 9. Do you get it? So that's the same thing we are doing here. Okay. So the address you are trying to access is what? 10110. Right. But realize that we are using an 8 block cache. The cache has 8 memory addresses. So the last 3 bits, 110, is what we are using. Right. Now we come to 110. Right. This is the first time we are using the cache actually. We come to 110. Now the first time you're accessing to always be a miss. So that's why a miss is here, right? The first time you access it will always be a miss. So we'll miss it, right? But because the first time you access, we'll set the validity bit what? Yes or true. Then the tag. The first 3 bits are used, so the remaining bits are used for the tag. So that's why you see the tag as what? 10. Right? And the data, which data will it store? The data at this memory address. Right? That's why it's mem of this one. Now you can try another access. Another access you are trying to access, we come to the cache again. We are trying to access what? 11010, right? So the last 3 bits is 010. So go to 010, right? Now this is the first time you're accessing, so it will be a miss, right? So we'll set the validity bit to what? Y. Now the tag will be 11 because the first 2 bits is 11. And what data will it contain? It will contain the data from this memory location. Now we are trying to access the cache again. So this time we are trying to use this address, right? Now we come, you see this is 10010, but this one was what? Okay, I thought it was the same. Yeah, we are okay. This is 10010. This is also a miss because it's the first time you are coming to the cache, right? It's the first time you are coming to the cache, but see, although it's the first time you are coming to the cache, right? This index 010, someone is already there from the previous part, right? So what we do is that we overwrite it because you are the most recent person coming to the cache, right? So this will be a miss. Even though there was data there, the data was not right because when you check the tag here is what 10, but the tag here is what 11. It's not the same, right? So the data there will be a miss, right? So that's why we have to overwrite it, right? And that's what you see here. Now, if the person comes again to try and do this again, this same memory access again, it will also be a miss, right? So if you want problem of the direct cache, if you access alternating how do you call it? Continuously, you'll be continuously missing. Then the next one is for this. So this one is also 110, right? But the first two bit is what 10. This one is also what 110. The first two bit is 10. So it's the same thing actually. So this one will be a hit. It will not be a miss, right? To be a hit, it's not be a miss. So this one will go to CPU, right, directly, and that's all the.
What's the difference between the hit and miss?
The hit means that it is in memory, like it is in cache. When we went to search the cache, we found it. The miss means that we couldn't find it. Then a direct map cache. So we are trying to see the direct map cache, right? So you realize that um in MIPS architecture, right, we have 32 bits. I mean, the word size is 32 bits, right? Our data is 32 bits. Now, you realize that part of it will have to be used for the index to know which block of the cache to even go to. Because, I mean, all these parts can be storing your data. So where do you know where to go to? So we have to know the index, right? Now, we also have to know the tag, right? All these parts can be storing the data, but remember that in direct map, two locations in memory can map to the same place in cache, right? So it means that we need the tag to know which one exactly we are talking about. We also need the validity bit, right? Before we need the what data itself. The data is usually 32 bits, right? It means now all this time we are dealing with only a cache storing one word at it. So sorry. And I said they said the cache is what 1024 or it's one word block, right? So 1024 one word block means that the total number of addresses or blocks or locations available for storage in cache is what 1024, right? But one word block means that the data is what one word, right? Sometimes we can have multiple word block. We can have maybe four word block, right? So maybe when we go to memory, instead of fetching maybe from location 0 alone, we can fetch maybe from location 0 to location 16. And that one, the data will not just be 32 bits, it can be like 128 bits long, right? Then we use multiplexer to choose the section of the data, but that's complex. We will see that later. And now this is the logic for checking a hit, right? So it is a hit if it is valid, one, and the tag corresponds, right? As for the index, you always get the right index, right? Because yeah, you know the place because like you specify it in your address. Now, this is some details, right? We have times when our cache we implement it on instruction memory or data memory, right? Now, when your cache misses on instruction memory, what you have to do is that you send the original program counter value, right? That is PC minus 4 because usually it is PC plus what I have. As you send it to memory, right? So you send it to memory. Then you instruct the main memory to perform read and wait for the what? Complete access, right? So what he's saying is that when maybe you'd expected some instruction address to be in cache already. Now you went to cache, you didn't find it. Then you have to go back to memory, right? But you have to go back with the previous program counter value, right? And know what to do, right? So after read complete, you put it in cache memory, then you start the instruction. Now for data, you handle it differently, right? So it is similar to the instruction, right? But to reduce the data miss penalty, you allow the processor to execute the instruction while waiting. So this is a one mechanism, but we'll see that. And think let's take a read at this. The reading is plenty. So the yeah, I think this one is no different. So the first one was um 1024, right? This one is what 16K words cache. Right? I don't think it's any different from that diagram. Now there are schemes, writing schemes, right? When you miss, right? So for example, you have fetched something in cache, right? And maybe you are storing word, right? So maybe you fetch memory location 100 into cache, and now you are using the store word instruction. Now remember, if you go and write it only to memory, what about the one in cache? You have made mistake, right? And if you write it only in cache, what about the one in memory? So there are two schemes. There are write through scheme, right? Which you write to memory and come and write to the cache. And there's what the write back scheme as well, right? And there are also mechanisms to prevent delays, right? Especially for the scheme. So this is just a bunch of video. You will get it, especially when you get the video on that one. So we are trying to take advantage of spatial locality, right? So you see that the first one, right, it was actually taking advantage of temporal locality, right? So it says what kind of locality are we taking advantage? This one is temporal, right? Because I mean the memory we have access, there is high probability that we access it again, right? Now if it was spatial, this one, how should I say it, wouldn't have been very optimal, right? It wouldn't have been very optimal because it doesn't even show any kind of spatial something. But this one is optimal for spatial because when we are fetching, we fetch more than one block. We don't like more than one block of data from memory. We don't fetch only one. So, for example, if you had this in memory, I mean this in memory, right? And you were coming to fetch data to the cache. Usually, you fetch only this one for the one block cache. But if it's a four block cache, you fetch four. If it's a four word cache, you fetch one, two, three, four. You fetch all these four and send it. Even though that originally we were looking for only this, but I fetch all the four and send it, and that's spatial locality, right? Because there is a high chance that the next time you'll be coming here, especially for instructions, right? Because when I always PC is what PC plus four, PC plus four. So if you do spatial locality for instructions, right, it will really help you, right? So this is taking an advantage of spatial locality, right? So they say that this is a cache with 4K, right, 4 word blocks, right? Bytes offset is ignored next to bits. I'll explain that later. But what they are saying is that it makes everything is word aligned, right? And a word is um 4 bytes in it, right? Which is 2 bits. Yeah, a word is 4 bytes in it, right? Which is 32 bits, right? Now, how do you call it? Because it is 4 bytes, right? The first two locations, right, is called bytes offset when we are trying to use an address to access it. So we don't usually use it. Right? So the first two, right? But when you have an architecture which uses maybe instead of 4 bytes, it uses 32 bytes, right? Then instead this time you not use what the first 2 bits, right? You use what the first 5 bits, right? Because that's the byte offset of the architecture, right? We'll see a question of that, so don't worry. Um, so so yeah, you can also like just like the multi word one, right? So this has multiple word, right? So this one you will also have a way to what check the correct word which you are talking about, and we'll see that later, but don't worry. So there is also replacement scheme for multi word blocks, right? I mean, supposing that you came to check and you realize that this is not what you need, right? But it is something far from this one. How are you going to change this whole 4 word block? So what are you going to do? There means they say that if write hit, the tab requested or address and cache are equal. Continue as for one word block by replacing the block. If it's a miss, that is the tag are unequal. Replace the word across the mix and write the block both to cache and memory. Right. So what they are saying is that if you want to write, right, and you realize that that block I want to write to is already in memory for a multi-word block cache, right? What you do is that the you continue just like the way you do for one word blocks, right? you replace the word and you write the block back to memory. So, for example, if it is only this word that you were writing to, maybe you were doing store word, and when you come to the cache, you realize that, oh, that word is already in memory. So when you write to only this block, right, you have to write the whole block back to memory, right? Now, if it's a miss, right, you came to the cache and you didn't find it, right? If it's a miss, and that's the tag or equal, then you first fetch the block from memory, replace the word that caused the mix, and you write it back towards both the cache and memory, right? So you fetch first, you replace before you write it back, right? I know it's abnormal, but that's how they do it. So unlike the case of one word block, a write mix of multi-word blocks causes a memory read, right? There will be a memory read overhead. Direct map cache. So we have seen one thing that if you take advantage of spatial locality, that's the possibility that the memory locations you access are close to each other, right? And the it will increase. Realize that when we do this, there is some statistics on it, right? So realize that miss rates falls, the rate at which we miss falls with increasing block size as expected. But as block size become a large fraction of the total cache size, the miss rate may go up, right? What it's saying is that initially, right, when you start increasing the number of blocks in your cache, right, the number of blocks, because of you are taking advantage of spatial locality, the miss rate will fall, and that's what it's saying. However, it will not fall forever. At a point, it will start rising again because a significant part of your cache, right, a significant part of your blocks will be in memory already, and it's not fall forever because you have very large blocks in them, right? And when you have very large blocks in memory, there's possibility of computation increases because yes, it's true that memory is spatial, but at a point in time, it's not really spatial. Sometimes we jump to locations right, and that overhead will be it will hit you very hard because you have large blocks. And another thing is that sometimes block will get ejected before most of their words are accessed. So, for example, you might have fetched all of these four, right? But maybe most of the time it is only this one which is accessed before the whole thing is trashed again, and that's called trashing, right? Cache trash. But let's see a problem about cache, right? Most of them are reading and explanations. I think I'll do that one better. But let's see an example of cache. So you have a cache, and they are asking you that how many total bits are required for a direct map cache, right? And the direct map cache um, has 128 kilobytes of data, right? When you see capital B is kilobytes, and one word block size, assuming 32-bit address, right? So let's take it step by step. Now, I hope you know that kilo, right, in binary is the same as 2 raised to the power 10. Do you understand? Do you know that already? Kilo is 2 raised to the power 10, mega is 2 raised to the power 20, giga is 2 raised to the power 30, right? And you keep on increasing. Now, 128 is also 2 raised to the power 7. Do you know that? 2 raised to the power 7 is 128. 7. I think 2 raised to the power 5 is 32. 6 is 64. 7 is 128. So 2 raised to the power 7 times 2 raised to the power 10, that's 2 raised to the power 17 indices, right? So that's the total number of bytes you have, right? But remember, you are storing words, not bytes, right? In memory, when we are talking about memory, we talk about memory in bytes, right? But when we are fetching memory, we talk about it in words. Okay, so we are storing words, not bytes, and it is a one word block, right? How many words make up how many bytes make up one word? 4 bytes, right? 4 bytes. So we have to divide this one by what? 2 raised to the power 2. I mean 4, or we have to divide it by 4. When you divide this one by 4, you get this one. I hope you know that. You can do that one. Yes. So it means that this cache has a total of what? 2 raised to the power 15 blocks, right? So it has like the cache, it has that line like 2 raised to the power 15. So this lines in the cache. these lines, one, two,
Mm.
up to 2 raised to the power 15. That's what that answer means. Do you understand? Okay. Then the next part is um you have to find, see how many total bits are required, right? So what we want to do is that um most times when we are talking about cache, people ignore the other aspects, the other small aspect, the tag, the validity bits. They talk mostly about the data alone. You get it? So we have dealt with the data alone part, and we have seen that the storage is equal 15 blocks, right? So if you want a cache of 128 kilobytes of data to store only of data, you need 215 blocks of what? Uh, Cache, right? However, there are other components of cache which not accounted for. One is the data. Okay, the data bit is accounted for. Then the data itself, right? One is the tag, and one is the validity. You understand? Now, since we are using 32-bit addresses, I mean we are in a 32-bit architecture. So it means that the number of data bits in the data is 32 bits, right? Be careful of the how do we call it? The units, right? Now, how much do we use for the tag? Remember, the cache has 2 raised to the power 15, 2 raised to the power, I think, yeah, 2 raised to the power 15 blocks, right? So how many lines or how many bits do you need to represent 2 raised to the power 15? 15 bits. We need 2 bits to represent 2 raised to the power 4. We need 1 bit to represent what? 2 raised to the power. We need 2 bits to represent 2 raised to the power 4. We need 1 bit to represent 2 raised to the power 1, right? Or, sorry,
Need to be to represent series very powerful.
yeah, because 2 raised to the power 4, yeah, like 4 different elements, 0001, 110. Do you understand? Yes, we need 2 bit and 1 bit to represent 2 elements, 0 and 1, right? So only 1 bit can differentiate 2 elements. That's what I'm actually saying. So because there are 2 raised to the power 15 different number of elements, right? We will need first, we realize that the address, the whole 32-bit address that will come, this 32-bit address, this one, we will not use all of them. We will not use all of them for one thing. Some of them will be used for the index. And how much has it been used for the index? There are a total of 2 raised to the power 15 locations. So we need 15 bits for the index to be able to span that location range. So that's what you see. So 15, right? So the 32 is the total number of bits in the address. The 15 is the total number of bits uh, in the index, bits in the index. Now remember, the cache, it was measuring in bytes, but remember we are using words, right? So this uh, byte offset, it has to be there. Remember that the first 2 bits we don't use it, so you have to take account of them. Do you get it? Mix is what word addressable, right? And each word is what 4 bytes. 4 is what 2 is the power 2. So that 2 you see, you have to also what account for it. So in total, how many tag bits do we have? The tag is actually the remainder after you have subtracted all those small things. So 32 minus 15 minus 2. I think this is 32 minus 17. 15. It will be 15. Okay. So you have 15. Now remember, in a cache, there is also the validity bits. So this part is for the tag bits. What we did here is calculation for the tag bits. There is also validity bit. The validity bit is that bit which shows that it is fresh like data. You can access it. That 1 bit here, right? So that is the one, right? Now when you do all that, you realize that you get a total of what 48 bits. So it means that for the cache, each line, let me use this cache because this is a one word cache. The cache, each line for this cache you're implementing, each line will use what 48 bits, right? We need 48 bits, 48 bits, 48 bits, 48 bits. Do you understand it? Yes, and that's what we are implementing now. You realize that this is not the, so 48 bits is that each line in the cache is 48 bits, right? But there are a total of what? 2 raised to the power 15 blocks in the cache. So what is the total size of the cache in bits now? Would what? 2 raised to the power 15 times what? 48. And now they have just converted it and it says it will be what? 1.5 megabits. But I mean, there are several ways you can do it. So 2 raised to the power 15, 48 is the same as what? 32 plus 16, right? Now, 32 is the same as 2 raised to the power 5, 16 is the same as 2 raised to the power 4, right? Now you can factorize 2 raised to the power 20 from this, right? Or you can just expand it. So when you expand, you will get 2 raised to the power 20 plus 2 raised to the power 90. Now you factorize the 2 raised to the power 20 out, you get 2 raised to the power 0 plus what? 2 raised to the power minus 1, right? So they are just trying to just actually factorize it so that they will get a multiple of, should I say, 10 in the power of 2. Because you realize that when you have 2 raised to the power 10, it is kilo. 2 raised to the power 20, it is mega. 2 raised to the power 30. So that's what they are trying to do. Trying to get a multiple of 20, 30, 10 in the power. So when they realize you get what? 1.5 megabits of data. That would be needed for the class. However, when we are considering only data, our cache, we wanted the cache to store 128 kilobytes of data. So we are considering only data, right? It is kilobytes. So we have to convert it to bytes, right? So we multiply by 8, right? Only data, the only data side is here. Here, this side is the only data side, right? It will store the actual data you want to access. This whole part is just to help you get the right location. So only data, when we are considering only data, would have needed what? 1.5 megabit, right? I mean, because it is 128 kilo times what? 8, right? You can just do that. So this is 2 raised to the power 7 uh, plus times 2 raised to the power 10 times 2 raised to the power 8. 2 raised to the power 3, you get 2 raised to the power 20. 2 raised to the power 20 is the same as megabits, 1 megabit. So now what they find out that when you find the ratio, you get 1.5, right? It means that it cost us like 1.5 times more data was needed, right? To store those unnecessary things, right? Those unnecessary things that will help us to get the right data, right? 1.5 times. So that's usually most people when they implement cache, they check this one, right? And it's a performance measure for the cache, right? And there's another question, right? I think when we solve this one, we can close. It says how many bits are required for a direct map cache, right? And this direct map cache has it is supposed to store 128 kilobytes of data, right? But this time we are using 4-word block size, right? And we are using the 22-bit address space. The first time we're using what? One word. One word. But this time we're using 4-word, right? So how do we solve it? The same thing, 128 kilobytes is the same as 2 raised to the power 17 bytes. We are aware of that. Now, we are now in bytes, but we have to talk in words. So we have to divide by 4. When you divide by 4, you get what? 2 raised to the power 15. Fine. However, this cache is not like the first one, where each one was just storing like only one line of data. No, this cache is storing like 4 lines of data. So there's another one of this one. So 2, there's another one of this one. 3, there's another one of this one. 4.
Each of them being 32 bits.
32-bit, 32-bit, 32-bit. Do you understand it? So that's what is so that's why this is called 4-word. But this is 1 word, this is 2 word, 3 word, 4. So it's 4-word. So for example, so that cache is typically like this. 4-word, 1, 2, 3, 4. It's a 4-word cache, right? And so because it's a 4-word cache, right? Even though we have been able to divide to see the number of blocks, it is not entirely correct, right? Because the number of blocks is actually supposed to be spanning all of this space, right? So we are going to store 4 of the words in one block, everything. So it means that the number of words we have found, we are going to stack the words into 4s, like 4 words at a time. So we have to divide by 4 again, right? I'm sorry, I think it is. We have to divide the 2 raised to the power 15 by 4 again. And this will give you what? 2 raised to the power 13, right? So it means that the actual number of blocks, the actual number of lines will be 2 raised to the power 13, right? Now, once you get that, you are through with the question. However, we also have to find a cache entry size. This will not be like the first one. Realize that the first one, the data part was always what? 32, right? Because we were storing one word at a time. The first one, the data part is 32 because we were storing only one word, right? But this time, the data part will not be 32 to be what? 4 times 32, which is 128, right? And that's what you see. So the data will be what? 4 times 32, 128, right? Now, what will be the tag bit, right? There, here, um, the total number of bits in an address is 32 bits, right? Now, because you have 13 blocks, you'll be using 13 bits for the index. Fine, we understand. You will not use 2 bits for the byte offset, right? Now, there'll be also another extra 2 bits, which you will not use because this is forward, right? So you need 2 bits to select the right word, even when you find it. So that 2 bits is what will go here. That 2 bits will go to the multiplexer, right? And that 2 bits will come to the multiplexer to either select this word, this word, this word, or this word. You understand? So when you so this one will be what? Minus two again, right? And 1, 2 for the byte offset. The byte offset is always emails is always 2, so it will be there. But this extra 2 comes when you have multiple words, right? And this 13 is as a result of we having 13 blocks, right? So this one will help us to find what the number of bits we'll be using in the target, right? So I think you can do it then plus one validity bit, right? I mean, no matter the number of words you have, you always have one validity bit. So that's what you see. When you do this, you get 144. Now, you go through the same approach to express 144 in terms of, how do you call it? In terms of exponents, right? Something exponent 2, right? And realize that they came to get what? 1.125 or megabits, right? And this one is just math. You can do that one. Now, once you're able to do that, you can also find the ratio, the original cache size to the data size now. Then you realize that this is what 1.125, right? And it says that one. Okay, let's solve this last one. Then we will not solve again. So this last one says that consider a cache. The cache has 54 blocks and a block size of 16 bytes. Right, so each block size is what 16 bytes, right? Mm, yeah, 64 blocks, right? And a block size of 16 bytes. So then it's like the data side is 16 bytes, 16 bytes of data, 16 bytes of that. So these questions keep an open mind. Don't always assume this. What block number does the address 1200 map on? Right now, I think they are using direct mapping, right? So what they are talking about is this. Maybe you see I said memory is addressed in bytes, right? So maybe the divisions you had byte 1, byte 2, byte 3 are up to byte whatever, right? Now you have byte 1200 somewhere here.